Okay, we're going to talk about material from lecture 6. It's on measures of variability or dispersion or spread, how spread out the data is. We're going to have 3 such measures in this section: the range, the variance, the standard deviation, and a little later we'll see a 4th one called the interquartile range. These measures of dispersion or spread or variability are for univariate quantitative data, that is to say, lists of numbers, right? The usual sort of numerical or quantitative data. The idea is, I need to stop and say, as usual, that these videos, watching these videos, is not a substitute for reading the book and notes. Right? That's primary. This is supplemental. All right. Take a look at these 3 data sets that are graphed here. They're also listed. But this data set, all the numbers in it are between 3 and 11. Right? The data is all bunched up right in the middle. This data set, well, it's spread out a little bit wider, and it's a little thin in the middle. And this data set, it's spread out much wider, and there are 3 clumps of data with basically nothing in the middle, just a couple little values. All of these have mean and median 7. Right? For all of them, the mean is 7 and the median is 7. Right? So the mean and median really don't tell you very much about this data. They tell you where the center of it is, but they don't tell you very much more than that. So we want some measures of how spread out this data is. And the first one, the simplest one, is called the range. Right? The range doesn't have any particular symbol. Some people just use an R, but that's actually a bad idea because R's usually means something else in statistics. Anyway, range is very simple. It is just the maximum value minus the minimum value. That's all it is. And so for this first data set, for example, the maximum value is 11, the minimum value is 3, so the range here is 11 minus 3, or 8. This one, maximum 12.75, minimum 1.25, so the range is 11.5. And then finally down here, and this data does take up a little bit more of the number line than this one. And then down here, of course, the range is much larger. The range is going to be 30 minus negative 16.9, this minimum data point here, and that is 46.9, right? It's spread across a range of 46.9 on the number line. It does look like, the more spread out the data is, the larger the range is. And that's true, all right. But it's not enough. It's not enough information. Right? Because look at these 2 pictures here. These are both pictures of data in the range, let's say 0 to 100. Right? This is 2 different axes. Both data sets have the numbers 0 and 100 in them. But this data set up here, all the rest of the data is right in the middle. And this data set has data spread out all the way across. But they have the same range. So these are still very, very different sorts of data sets, but they have the same range. The range doesn't really tell us what we need to know, which is really how spread out the data is. Clearly this data is much more spread out than this is, except for those 2 little endpoints, the 2 points on the end, but the range doesn't tell us that. The range is exactly 100 in both cases. So we need something better. And the thing we're going to look for is a measure of dispersion or spread that tells us how spread out the data is from its mean. If you look at the mean of the data, let's suppose the means are about the same in both cases here. Okay? This data is not very spread out from its mean. I mean, there's a little bit that's far away, but most of it is not far away. In this case, there's a lot more data far away. The average distance of a data point in this data set, on the top number line here, the average distance between the mean, and let's suppose it's sample data and call the mean x bar. The average distance between the mean and a data point is going to be pretty small. Over here, that's not going to be true. The average distance between the mean and some other data point is going to be pretty large compared to this. Okay, the two measures we're going to look at that measure the kind of the spread away from the mean, the spread of data away from the mean, are called the variance and the standard deviation. They're very closely related. The standard deviation is really just the square root of the variance. And in this course, we mostly calculate the variance in order to get at the standard deviation, because it'll be the standard deviation that we really use. And you'll see why we do that. But you have to be able to do both, and you have to know the relationship between them. Okay, here's a little preliminary to learning about the variance. If x is a data point, and we're only talking in this whole section, we're only talking about numerical data. If x is a data point or data value, then the deviation of x, it's really the deviation of x from the mean, but I won't write that out. The deviation of x is x minus x bar, right? X minus the mean. If it were population, of course, population data, you'd write x minus mu, but we usually just write x minus x bar. Okay. Deviation of the mean, deviation of x is just the distance between x, the data point x, and the mean. If this is the data point x right here, right, it would be this little distance. If this were x over here, then it would be this little distance, and so on. But these distances are signed. If x is to the left of the mean on the number line, then x minus x bar will be negative. And if x is to the right of the mean, x minus x bar will be positive. The reason I mention that is because when you're looking for a measure of how spread out data is from the mean, it makes sense to look at kind of an average amount by which data points deviate from the mean, right? How far are they from the mean on average? Well, it turns out that if you average all the deviations together, right, what would you do? You would sum them up. Remember, capital sigma means sum. You would take x minus the sum of all the x minus x bars, the sum of all the deviations, and you divide by the size of the data set. This is sample data, so I'd write the size as a small n. It turns out that that's always 0, and that's because of the way the mean and the deviation are defined. The next thing you might think of, and it would be a very sensible thing to think of, would be to take the actual distances, like x, the absolute value of the x minus x bars, and average those. That would not be 0, and you would actually get something that is useful. But it turns out not to be the very best thing that can be done. The best thing that can be done is to use a sort of average of the squares of these deviations. And when you do that, let's do it first for sample. You're defining the sample variance. The sample variance is you take the squares of the deviations. Now a deviation is x minus x bar, so its square is x minus x bar squared. And then you divide by, well, it's not quite the number of points in the data set, in the sample. It is 1 less than that. So you take the sum of the squares of the deviations and you divide by the sample size minus 1. And you get the sample variance. And the symbol for that is s squared. To define the population variance, it's not quite the same thing. You do take the sum of the squares of the deviations, these x minus x bar squared things, and you add them all up. And then you divide by the actual population size, not 1 less than the population. The reason you divide the sample one by n minus 1 instead of n is that it turns out that if the sample size is small compared to the population, which it usually is when statistics is actually useful. When the sample size is small compared to the size of the population, then using n in the denominator here ends you up with a biased estimator. That is to say, this s squared thing will not properly estimate the population variance, which, by the way, is called sigma squared. That's a lowercase Greek sigma. And so you use n minus 1, and that's not very hard to prove, but we won't do it here. All right. There is a problem with the variance. The variance does vary beautifully with how spread out the data is in general. Right? The variance of this data set would be much, much smaller than the variance of this data set because this data set is much more spread out, and that's exactly what we want. But there's a big problem with the units. The units of the variance, are the units of the data squared. Right? So if your data is measuring distance between things in feet, let's say, then your variance comes out in feet squared, square feet. And that's pretty hard to interpret. I mean, what you're looking for is a kind of average deviation from the mean. It doesn't make any sense for it to come out in square feet instead of feet. It's even worse when your data is something like the number of shoes in people's closets, right? Then your data comes out, then your variance comes out in shoes squared, which you can't make any sense of. The cure for this is to switch to the standard deviation instead of the variance. So that's what we will do for the most part. The sample standard deviation, right? The symbol for it is S, and it is simply the square root, the positive square root of the sample variance. And the population standard deviation, which is called sigma, is just the square root of the population variance, the positive square root again. Okay? And that is all there is to it. And the units of the standard deviation are the units of the data. Okay? So it will make sense to interpret the standard deviation as an average deviation from the mean. And in fact, I'm going to actually say that you should do that. Interpret the standard deviation as an average deviation of a data point from the mean. Okay. Well, we're actually going to use the TI calculator most of the time to compute standard deviations in this class, whether sample or population. But sometimes we will have to do it by hand, and you'll especially have to do it by hand in this section, in its homework, and on the test that tests this section. It's important to know where the standard deviation comes from. Okay, here's an example of doing that. To estimate how much change people carry around in their pockets or bags, Jake asked 5 randomly selected people how much they had with them. The responses were, well, these numbers. Find the mean, variance, and standard deviation of this sample and interpret the standard deviation. Okay. So I make this table to make my calculations, to organize my calculations, to make it all easier. Right? I put the data values in the left-hand column. Right? There they are, $1.50, $1.70, and so on. The second column is going to be the deviations. Right? And the third column is going to be the squares of those deviations. Now, since I need x minus x bar, the first thing I have to do is to compute x bar, the sample mean. And you know how to do that already. You just sum up all the data and divide by the number of data points. In this case, it turns out you get 1.9. So in this row, when x is 1.5, x minus x bar now is 1.5 minus 1.9, which gives you negative 0.4. And similarly here, negative 0.2, this one's 0, 0.2, 0.4. Okay, now the entries in this column here are going to just be the squares of these. When you square negative 0.4, remember that you are squaring the negative number, negative 0.4. Right? The reason I emphasize this is because when you put this in your calculator, it's very tempting to hit the negative button, the minus button, and then hit 0.4, and then hit the squared button. And that will give you a negative 0.16. Right? That's what you don't want. Right? Because you don't want this, your calculator applies, remember the order of operations thing, the PEMDAS thing? Well, your calculator knows it too, and it will square the 0.4 before it applies the minus sign. So you don't want to do that. You want to make sure you're squaring the whole thing. This turns out to be 0.16, of course, when you square negative 0.4. So that's what this is, 0.16. This one is 0.04, 0.04, 0.16. And then we're going to want to sum up this column. And when you sum all of these, it turns out that they add up to 0.4. Okay. The reason you want the sum of all these, of course, is because that's the numerator in the variance formula. Right? Remember the variance formula, the sample variance, is the sum of the squares of the deviations divided by the sample size minus 1. And now I have this numerator. This is 0.4. And sample size here is 5. There are 5 different amounts. So 5 minus 1 is 4. This is 0.4 over 4, which is 0.1, 1/10. So that is s squared, 0.1. And now to get s, the sample standard deviation, all I have to do is take the square root of s squared. Right? And that turns out, well, that's an approximate thing. It turns out to be about 0.316, so that's what I'm going to put here. That's the sample standard deviation there. All right, let me ask you one more question. John recorded the weights of 300 randomly chosen apples, while Jane recorded the weights of 300 randomly chosen dogs. Which data set had the higher standard deviation? Well, it'll be the one with the most variation, right? The one with the most values far away from the mean. The weights of apples vary, certainly. There are smaller apples and larger apples, but they vary over a much smaller range than the weights of dogs. Right? There are dogs that are very tiny, down to a couple of pounds, and then there are those monster, dogs that weigh 100 pounds or more. So there's going to be a lot more variation in dogs than there is in apples. So it will be the it'll be the dogs, the set of dog weights that has the larger standard deviation. All right, that's it for this section.